Okay, so in the example, it says the height of a tree at time t is given by a twice differentiable function. I know you don't know what that means yet, but we'll get there. Where h of t is measured in meters and t is measured in years. So this is my function, it's in meters. This is my time, it's in years. Selected values of h of t are given in the table above. Use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning. So the term twice differentiable and the symbols h prime of 6 are concepts we'll be taught later. However, h prime of 6 is like asking for an instantaneous rate of change using the approximate average rate of change because we don't have a function. So without a function, to get the derivative, we're going to approximate using an average rate of change. So what we're going to do is use that information to find the derivative. So h prime of 6 is equal to the value to the right of 6. So we're going to do h of t of 11 minus h of 2 all over 7 minus 3. Sorry, not h of 11, h of 7 and h of 3, which are 11 and 2. So 11 minus 2 is 9. 7 minus 3 is 4. So we get 9/4 as an approximation. Now we could get closer to 6 by picking 6 and or 11 and 2. So we could get closer. So now instead of 7 and 3, we'll do 7 and 5. Oh, I'm realizing you can't see it there. Because 6 sits right between 5 and 7. So we'll do h of 7 minus h of 5 over 7 minus 5. Now we get 5 over 2 and 9/4 to 5 over 2. You can see this is getting a little bit quicker. And our units for h are meters, time is years. So what that means is that the tree is growing at a rate of 5 meters every year at 6 years old. The 9/4 is an approximation because it's further away from the 6. So the closer and closer you get your approximation values to 6, the better your approximation. Okay, so again, this is average rate of change used to approximate instant. Since there is no function given. March. All right. Today we are looking at the second part of, so does the function 1 over x have a horizontal asymptote? If so, what is the equation for the horizontal asymptote? So if you think about the function 1 over x, in our minds, we should kind of visualize this function. We know for certain the domain is all reals except x equals 0. So I know that it has a vertical asymptote at x equals 0. And then if you think about the values of x, if you plug in 1, it's at 1. If you plug in 2, it's at a half. 3 is at a third. And if you plugged in something like a half, 1 over a half is 2. So in the positive side, it's increasing and then decreasing. So it's increasing to the left of 1, decreasing to the right of 1. And then similarly, if you plug in -1, you get -1. If you plug in -2, you get -1/2. -3 is -1 third. And then if you plug in something like -1/2, you get -2. -1 third, you get -3. So if it has a horizontal asymptote, it usually means it approaches a value on y, but never crosses that value on y. Hopefully, looking at this graph, we see that there is a horizontal asymptote at y equals 0. Because the graph is approaching 0 on both ends, the fractions are getting infinitely smaller as the x values are getting larger in the positive direction. Therefore, there is a horizontal asymptote at y equals 0. And if you follow the table or the chart down below, you can see that as well. And just if you want to know, there's a vertical asymptote at x equals 0. So today we are going to talk all about horizontal and vertical asymptotes. That is our goal. All right, so something you kind of just have to memorize a little bit is the horizontal asymptote chart. If the denominator is a degree 1 greater than the numerator, then you will always have a horizontal asymptote at 0. If the denominator is 1 degree greater than the numerator, then it will be at y equals 0. And that's what happened in the last example. X is 1 degree higher than 1. If the degree of the denominator and the numerator are equal, then your horizontal asymptote is at their coefficients. If the degree of the denominator and numerator are equal, then the horizontal asymptote is at their coefficients. If the degree of the numerator is greater than the degree of the denominator by +1, then you have a slant asymptote. If the degree of the numerator is greater than the degree of the denominator by more than 1, then you have no asymptote. So today we're going to talk about infinite and finite limits. We're going to talk about the behavior of these limits as we approach infinities. An asymptote is going to always involve an infinity of some sort. So it's important to know that the symbol for infinity is used to describe the behavior of a function when the values within its domain and range outgrow the bounds of the graph. Recall that infinity does not represent a real number. Infinity does not represent a real number. And if you think back to the example we just looked at, 1 over x, we can make two observations about this function now. The limit as x approached infinity of 1 over x was 0, because as x was getting really large to the right, the graph was approaching 0. So again, as x was going to infinity, f of x was going to 0. Limits are a lot like end behavior from trig and algebra 2. As x was going to negative infinity, f of x was also going to 0. So that's what this limit is stating here. The reasons this occurs is because of the horizontal asymptote at 0. Horizontal asymptotes are always described as y-equal equations. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. Does that make sense? In this case, the horizontal asymptote in the first example would be y equals 0. So the limit as x approaches infinity equals 0. Limit as x approaches negative infinity of f of x equals 0. Let's look at two different examples. So if f of x equals x over the square root of x squared, well, what do we know about the square root of x squared? What's that equal to? Yeah, it's technically equal to the absolute value of x. Awesome. But in short term, it simplifies or reduces to x. So what can you say about the coefficients of the numerator and the coefficients of the denominator if the denominator is like the square root of x squared? They're equal. So as we look at the limit as x approaches infinity of x over the square root of x squared plus 1, it's safe to say that this is behaving like the limit as x approaches infinity of x over x, where exactly what we just said, the square root of x squared represents the absolute value of x. And what do you know about the absolute value of x? Yeah, it's positive, negative, right? So like to the left, it's negative. To the right, it's positive. So if we're looking as x goes to infinity, we're going to use the positive x. And if we look at the limit as x goes to negative infinity, it's kind of going to be like the negative x. So this becomes 1, and this becomes negative 1. Because again, the absolute value of x is really a piecewise function where the slope is x and negative x, and it's x for x is greater than 0 and negative x for x is less than 0. So it's the positive x for infinity and the negative x for negative infinity. So you're not really plugging infinity in. You're talking about the coefficients or the horizontal asymptotes. So this graph has two horizontal asymptotes, right? We have a horizontal asymptote at 1 and at -1. And remember that a graph can cross a horizontal asymptote. It cannot cross a vertical asymptote. So a graph can go through a horizontal, it cannot go through a vertical. So I'll show you, let me show you a graph. Graph what? All right. So I took the function that we're looking at right now and I put it into my graphing calculator. So if you look at the function we're looking at right now, pause, share, start video. This is the function we were just discussing. Can you see how there is an asymptote at 1 to the right and -1 to the left, but that the graph, well, in this case it doesn't, but if it was a negative function, it could have. This one might not do it either. Because it just inverted it. I will find you one that crosses the asymptotes. It is possible. But you can see how you have an asymptote to the left and an asymptote to the right, but they're not the same either. Cricket is very loud. Great. So yesterday we discussed special trig functions, and we discussed the limit as x went to 0 of sine x over x. What about as x goes to infinity of sine x over x? So, what do you know about this function? Well, you can kind of rip it apart, and you get the limit as x goes to infinity of 1 over x times the limit as x goes to infinity of sine x. So it's fair to say that since this graph has a denominator of 1 over x, that the degree of that denominator is going to be greater than the degree of that numerator because that numerator is encompassed into sine. Therefore, we are going to have a horizontal asymptote at y equals 0 because that sine x function is being quote unquote sandwiched by the 1 over x function. So the limit, and this is again kind of like another special function, the limit as x goes to infinity of sine x over x is 0. And if you think back about that sandwiched graph, it eventually teeters off on both sides. Does some crazy oscillations in here, and then teeters off to the sides. Hi. What would happen if you altered that slightly? What would happen if you altered that slightly? Yeah, so it is going to change that. And the idea is, again, limits can be broken up into parts. So the x would go below each function. It'd be the limit as x goes to infinity of 5x over x plus the limit as x goes to infinity of sine x over x. So here, x over x, those have the same degree. Therefore, the limit of a function with the same degree on top and same degree on bottom, it'd be 5 over 1. It's the coefficients of the variables. So in this case, that would be equal to 5. And we said the limit as x goes to infinity of sine x over x is always. Therefore, the limit as x goes to infinity of this function is equal to 5. That flows us into vertical asymptotes. Vertical asymptotes are going to kind of be like the opposite of the horizontal asymptote. For the horizontal asymptote, our limits were going to infinities. For the vertical asymptotes, our answers are going to be infinities. So for a vertical asymptote, we're examining end behavior. For a vertical asymptote, we're examining end behavior. We have to look for vertical asymptotes. You must always find the right-hand limit and the left-hand limit. You must always find the right and left-hand limit for a vertical asymptote. We also call that end behavior. I changed my notes. Do these still match your notes? I feel like I was supposed to switch PowerPoints. Yeah, there we go. Because here's where I added some stuff. To find out if a function has a vertical asymptote, we need to determine where the function is undefined. To determine if a function has a vertical asymptote, we need to determine where the function is undefined. To do this, if there is a denominator, you set it equal to 0. Graphs have vertical asymptotes when the denominator is equal to 0, thus creating an infinite limit. Right? So let's look at this example here. We have, what are the vertical asymptotes of this function? Describe the behavior to the left and to the right of each. The vertical asymptotes once again occur when the denominator is equal to 0. So you set x minus 3 equal to 0, thus giving x equals 3. And then for our behavior to the left and to the right, we're going to do a lot with looking at a sign chart. So x equals 3 is kind of like in the middle of your sign chart. And we want to look at what's happening to the left of 3 and to the right of 3. So something to the left of 3 is like 3.1. Something to the right is 2.9. We have to be relatively close so that we could see how the behavior is. And again, the only thing we care about is if the behavior is positive or negative. So if you plug 3.1 into that function, 2 times 3.1 is positive. 3.1 minus 3 is positive. So that means to the right of 3, my infinity is positive. If you plug in 2.9, 2 times 2.9 is positive. 2.9 minus 3 is negative. So a positive divided by a negative is a negative. So that means that that part of the graph is going to negative infinity. Just for extra practice, does the function 2x over x minus 3 have a horizontal asymptote? It does. Where at? Perfect. So that graph would have a horizontal asymptote at y equals 2. So again, that would mean that the limit as x goes to infinity of f of x is equal to 2. And then the limit as x goes to negative infinity of f of x is also equal to 2. Good? Do we see the difference between the vertical and the horizontal? Okay, let's look at this example. We have 1 over x squared. Where's my vertical asymptote? Okay, what's happening to the right? What's happening to the left? So that's like plugging in 0.1 and negative 0.1. So anything squared is always right. And then the numerator is also always, because it's just a number. So both of these vertical asymptotes go to, excellent. Yes. Yeah, one's not prime. Yes. Yes, 0 is considered even. Yeah, they're all empty. We'll pause in a minute. All right, because the values of the function approach infinity on either side, we can say the limit as x approaches infinity, or the limit as x approaches 0 of 1 over x squared is infinity. So left-hand limit equals the right-hand limit, therefore the limit is infinity. In the last example, there was no limit because they went to opposite ends. So in the last example, the limit as x approached, I believe it was 2, did not exist because they went to different areas. Okay, how about tangent? What do you know about tangent? Yeah, so it has like a bunch of infinite vertical asymptotes though, correct? Exactly, once every period. So tangent, if you look at that though, what's your denominator of tangent to find the vertical asymptote? Exactly. So if f of x is equal to tangent, tangent's really sine over cosine. Therefore, the vertical asymptotes occur when cosine x equals 0. So cosine x equals 0 at 90. Yep. At pi halves, 3 pi halves, so on and so forth. So it would continue. It would go to like 5 pi halves and then 7 pi halves. And technically it could be at negative. Yeah, so exactly. They're in an infinite number of vertical asymptotes because it doesn't have a beginning or an end unless you have a restricted domain or range. So that means that the vertical asymptotes technically occur at x equals pi halves plus, how do you get from like pi halves to 3 pi halves or pi halves? Yeah, you add 1, right? So we're going to say at k pi, because they have to be like terms, where k is a what? It has to be an integer, right? It can be positive or negative because you can subtract, but it has to be an integer because, like you said, it has to be a whole number. So we would say that the limit as x approaches a from the right of tangent is equal to, and the limit as x approaches a from the left of tangent is equal to. So it's easy enough to look at pi halves. And if you think about sine or cosine, smaller than pi halves would be like your 0, your quadrant 1, right? Bigger than pi halves is quadrant 2. All values in quadrant 1 are what? So, in quadrant 2, sine is positive. So that means that as you approach pi halves from the left, which is quadrant 1, it's at positive infinity. And if you approach pi halves from the right, or quadrant 2, it's at, therefore, the limit as x approaches a does not exist. And technically, since I used a in my limit, instead of saying x equal, I should have made that an a equals pi halves plus k pi, so that a was representing my. All right, so this is like a good little pause point. The last thing we're going to look at is end behavior, and then we'll be good. So if you want to go see if there's water, you can. If you want to stand up, stretch, move your body, you can. And then we'll do the last few examples. So just take like 2-3 minutes. So you might see me label this as EBM, end behavior model, just because sometimes I don't want to write it all out. But the end behavior is, what is that graph doing? So we talked a lot about horizontal asymptotes today. An end behavior model is a way of looking at a horizontal asymptote for really, really complicated functions and simplifying it. So we could say that the function g is a right end behavior model for f if and only if, as you go out into the infinities, their functions equal 1. Or as you go into negative infinities, their functions equal 1. If a function provides both a left and right end behavior model, it is simply called an end behavior model. So we're going to look at examples of end behavior models and just talk about how they can be used to help us understand complicated functions on a more simpler note. So comparing f and g, we have 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. And we have 3x to the fourth. If we put these in our graphing calculators and you zoom out, what you'll notice is that in normal mode, they have a gap. And then as you zoom out, that gap closes. So I can graph them. Okay. So what you'll notice is initially there's a pretty decent gap between them. They don't look anything alike. But then as you zoom out and out and out, So let's say my x's go negative 20 to 20. We'll say my y's go negative 5. If I make those numbers a little bigger, it'll graph quicker. Okay, so remember the blue one was the original. The red one is y2. Now, as we zoom out, can you even tell that they're two graphs? No. So since as you zoom out really, really, really far, if the graphs behave the same, then they have the same end behavior model. And it's fair to say, where are both of these graphs going as x is getting big and y is getting big? Yeah, they're both going to positive infinity. Y equals 3x to the fourth. This is what type of function? Yeah, it's a quartic function, and quartic functions are, their end behavior is an even function, right? So if you think about the end behavior of even or odd functions, a quartic has an even end behavior. So even end behaviors go in the same direction. What the heck? Find an end behavior model for this function then. So 2x to the fifth is what type of function? But odd. And then, I don't know why. There you go. So we have 2x to the fifth, which is odd, over 3x squared, which is even. However, if you just compare the highest coefficient from the numerator to the highest coefficient of the denominator, they behave like 2/3 x cubed. I'm going to show you. So the end behavior of all polynomial functions will behave like the end behavior of their largest monomial term. So that means this function here, like we said, is odd. So it means it's going to behave like an odd function. This function here is even, so it's going to behave like an even function. However, if you simplify them and you take the highest of the top and the highest of the bottom, they behave like 2/3 x cubed. So that doesn't, which would be exactly odd. So this end behavior model is 2/3 x cubed, which means the limit as x approaches negative infinity and the limit as x approaches infinity will behave like x cubed. So as x cubed was getting more and more negative, this would go to negative infinity. And as x cubed is getting more and more positive, it goes to positive infinity. So all it means is that that function is ending in the positive and negative behavior. Doesn't mean it acts like a cubic in the middle. It just means that it goes in opposite directions when it talks about its end behavior. Does that make sense? What about g of x? They're both odd. And what do you know about the numerator and the denominator? They're both cubic, which means that g of x has a horizontal asymptote where? 2/5. The end behavior model is 2x cubed over 5x cubed. What happens to the x cubes? Yeah, so this end behavior model is actually 2/5. So what's that mean is as you look at the limit as x approaches negative infinity, where's it going to be going? Yeah, 2/5. And where's it going as it gets to positive infinity? Therefore, again, that horizontal asymptote came back into play. So not all end behavior models are going to be going to an infinity. Some end behavior models go to infinities, some go to asymptotes, some go to 0. And then we'll end with exponentials. These 4 limit values never change. These 4 limit values never change. You know what, we'll pause. We'll do the exponentials and absolute values tomorrow. Because tomorrow I want to review some more. I want to make sure we're A-okay with the end behavior and asymptotes. And I may just have to look at